Okay, hi guys. I'm recording this video because we cannot have an in-person lecture for the next class because I need to attend the international conference. Okay, so okay, please watch this video. Then, you know this part is very important, right? So actually, so in the pipeline architecture, so I mentioned that this topic is so important in this course. And then, so actually we learned about the concept of pipeline architecture. So, and then I believe it's not difficult, right? So actually, we can just split some hardware components by some execution steps, and then we can just insert the pipeline registers. So by doing this, we can reduce the critical path of this CPU architecture. And then, so benefit is that so we can increase the clock frequency of the CPU, and then which means we can improve the performance. So the the concept of a pipelining is simple, and then I believe that you can easily understand the benefit of the pipelining. But so actually in the pipeline architecture, so the clock cycles can be wasted because of what? The hazard, right? And then so these hazards need to be properly handled in the process architecture. So now we will learn how to handle data hazard in CPU, right? Okay, so what is the data hazard? So I mentioned that you can understand the hazard is an event that wastes clock cycles, right? So which means the next instructions cannot be executed by some reasons, right? So this is the hazard. And then what is the data hazard? The data hazard is caused by data dependencies, right? So this is the example. So you can find the data dependencies in this code. So actually the uh, so in this example, the solve instruction generates the result, and then it stores this result in x2, and then the following instructions like AND, or, add, and store instructions receive data from the solve instruction. Not receive, actually, it uh, uses they uses the data generated by the solve instruction, right? So you can find that the end instruction also uses the x2 and the or x2, 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 also x2 here, right? The four following instructions, so in this example, the four following instructions use the data generated by the solve instruction. So you can find the data dependency here. So this is data dependency, and data dependency, and data dependency. Then how can we handle data dependencies in the pipeline architecture? So actually we can reserve data hazard with data flooding, okay? Then what does that mean? So we need to detect these data hazard, the data hazard cases in the pipeline architecture, and then we need to apply the data flooding in order to address these data hazard issues, right? So, so you can, in this figure explains how the data can be boarded in the pipeline, the CPU architecture. Okay, so as we learned, the CC represent the clock cycle, right? Clock, and then the number represent the clock cycle number, right? And then this is the some flow of the 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 sequence of executions, right? The sequence of instructions, right? So the first dependency, the data dependency between the sub and add. So you can find that the end is right. So you sub and end, right? So you can find that the end instruction receive data from the sub instruction. So this is the very next instruction, right? And then actually we already learned how these data dependencies can be uh, handled in the CPU architecture, right? So we learned that actually the X2, so X2 is generated by ALU, right? So actually the data is generated, okay, generated at this time, and then for this end instruction, the next instruction, the data is required at this time, right? So if you just see this timing, right, then we already know that the end instruction can use the generated data, the data generated by ALU. How? This data can be delivered to the input of the ALU, right? Because in order to execute this end instruction, then the CPU requires this data just the before before the input port. So this timing, input port of the ALU. So the data can be forwarded. So for this data dependency, the data dependency between the very next instruction, the then so when the data is generated by ALU, and then to the next instruction, the data will be propagated to uh, the memory stage, right? So actually, on the rising edge of the clock, then this day generated data will be provided to the memory stage. So and then the sub instruction is in the memory stage, right? So this data this data can be forwarded, right, for the end instruction, right? So this data can be forwarded to the input of the ALU, right? So this is the data forwarding for the data dependency. Then how about this data dependency, right? So when the OR instruction requires the data for X2, right? Then where is the sub instruction? Sub instruction is in write back stage, right? Write back stage. And then this data is required by this OR instruction, right? So in this case, so this data is also propagated to the write back stage. So the X2 generated by the what is this instruction? Sub instruction is in the write back stage. So it's the very early time of the write back stage. So and then at the same time, the OR instruction requires the X2 data generated by sub. So this data can be forwarded to the input of ALU, right? So this forwarding, so for this data dependency, the data, the result of ALU, so in memory stage is forwarded to the input of the ALU. Then how about this data dependency? So for this data dependency, the data in write back, so actually, so data is propagated to the write back stage via this memory write back pipeline registers. So this data is forwarded to the ALU, right? Do you understand? Okay, it's a data forwarding. Then how about this data dependency? So you can find that the add X 14, x2, and x2, right? So in this case, when the sub instruction is in write back stage, then the add instruction is in id stage. Then for the add instruction, the CPU reads. So this is because the add instruction is in id stage, and then during this in this id stage, then CPU reads register data, right? But at the same time, then you can find that sub instruction is writing the result to the register file, right? So sub instruction is in the write back stage, and then this add instruction is in the id stage. Then how can we handle this this operation, right? So it's a writing, the sub is writing, and then add is reading. Okay, reading in register file and then writing to register file. Okay, so we assume uh, we assume that the register file supports the internal forwarding. So internal forwarding means that when the data is being written to the register file, and then at the same time, then the same data is being read from the register file, then if the register file supports the internal forwarding, then we can read this latest data, the data which is being written to the register file. So the data can be, so while the data is being written to the register file, then this latest data, this data can be also can be read from the register file. So it's called the internal forwarding, right? So we assume the register file supports the internal forwarding. So for this data dependency, so data dependency between the sub and add instruction, then we assume that the data can be forwarded inside of the register file, right? So how about the store instruction? The store instruction also uses the x2 data generated by sub instruction, but we can observe that this data was already written back to the register file, right? So which means the data exists in register file. So it's a write back. So sub instruction is in the write back at clock cycle 5, and then store instruction try to read data at clock cycle 6. So we can just read. So we can just read the data from the register file, right? So forwarding is not required for this case. So what can you observe? In order to handle the data hazard by data dependencies, right? So we need to support, actually the pipeline, the CPU needs to support the three different cases of data forwarding, right? So what are they? So first forwarding. The first forwarding is that, so this is the forwarding from memory to ALU, right? So so at CC4, so actually I already explained about the data dependency between sub and end, right? When the sub instruction is in the memory stage, then end instruction can receive the data from the sub instruction using data forwarding, right? So the first forwarding is the data forwarding from memory stage to the ALU, okay? The input of the ALU, right? So this is this case, right? So this is the first forwarding. Then what is the second forwarding? The second forwarding is this data dependency. The data dependency between sub and or, right? So what is the second forwarding? The second forwarding is the data is delivered from the write backstage because the sub instruction is in the write backstage, and then this data is forwarded to the input of ALU, right? So this is the second forwarding. What is the third forwarding? The third forwarding is the the internal forwarding in register file. so So sub instruction is in the write back stage, right? But at the same time, because this data is being written back to the register file, and at the same time, the add instruction is reading this data, right? So, the third forwarding case is the internal forwarding. Okay, so this is the internal forwarding. So we can figure out that in the CPU architecture, the pipeline to CPU architecture, then this pipeline, the CPU, needs to support these three types of data forwarding. The first forwarding is the forwarding from memory to ALU, and then the second forwarding path is the data forwarding from write back to the ALU, and then the third forwarding path is the internal forwarding inside of the register file, right? So the pipeline, the CPU, in order to try to sorry, so in order to handle the data hazard caused by the data dependencies, the pipeline, the CPU supports these three types of data forwarding. Okay, then let's see how to implement. So firstly, we learned the concept. Okay, it's just a concept or a scheme, right? So we just figure out the how the data forwarding is supported conceptually in a pipeline, the CPU architecture. Then we will learn how to design, how to implement this data forwarding in the pipeline architecture, right? So let's see how. Then how can we implement the data forwarding in pipeline architecture? So what is required? Firstly, we need to detect what? Forwarding cases. Okay, so firstly, we need to detect when the data forwarding is required, right? And then, so when the data forwarding is detected, right? So if the data dependencies are detected, then we need to apply. Okay, this is means how. Okay, we need to apply the data forwarding inside of the CPU, the pipeline, the CPU, right? Do you understand? Then, so if we can detect the data forwarding case, then we can just apply, right? Data can be just delivered, right? So then how can we detect? How can we detect these data forwarding cases? So how can you detect? So, okay, let's see this one. How can you detect? How can you detect? So it is simple, right? So when I explained about the data dependencies between instructions, right? So I just checked, oh, this is the data. So it's the destination register of the sub instruction. And then what is this? These are source registers of the following instructions, right? And then, you know, this is the boarding case 1, this is the boarding case 2, and then this is the boarding case 3. But we just ignored this case because we assume this third boarding case is automatically supported inside of the register file. Like, so this is the internal boarding. Okay, so we just ignore. So actually in the pipeline architecture, so we need to detect this first case, the board case 1 and board case 2. And how? So simply we can check the RD in sub, and then if the RD in this instruction is sub is equivalent to RS1 or RS2 in AND, right? So this is the first case. So what is the second case? Second for the case, RD in sub is equivalent to RS1 and RS1 or RS2 in OR instruction. So obviously, so we need to check the RD of the former instruction and RS1 and RS2 of in following instructions, right? So then, so this is the data forwarding condition, right? So this is the data forwarding condition. So we can just so this is the the first the forwarding case, right? It's a uh forward one, right? This is the forward two, right? So what? So obviously, so for the forward one, so I mentioned that the data is forwarded from memory stage to ALU. Where is the ALU? ALU is in the EX stage, right? So the former instruction is in the memory stage, right? And then the following instruction is in the EX stage. So, and then we need to check the RD of the former instruction. And then what is this RD? This is the, so it represent this is the RD in memory stage, okay? Because, the RD can be propagated to the, the next stage via the pipeline registers, right? Then we need to check the RS1 and RS2 in EX stage, right? So this is the RS1 and RS2, RS1 or RS2 in EX stage, right? So, this is the pipeline register, right? So after and then this means that it's the output of a pipeline register. So we can just think that this is the RS1 and RS2 in EX stage. So if this RD is equivalent to the RS1 and RS2 of EX stage, then we can think that, oh, this is the boarding case, which boarding case 1, right? Do you understand? And then what is the sec forward case 2? So obviously, so for the forwarding case 2 is that is the data in write back is forwarded to the ALU, right? Input of the ALU. Then what is this ALU? ALU is in the EX stage. So simply, and then with the same way, So we need to check the RD in write backstage with the RS1 and RS2 where same EX stage, right? This is the board 2 case. So it's a simple, right? It's a basic condition is that. So in order to detect the boarding case 1 and boarding case 2, we need to compare the RD in memory stage and RS1 or RS2 in EX stage for the boarding case 1. And then for the boarding case 2, we can just compare the RD in write back stage with the RS1 and RS2, or RS1 and or RS2 in EX stage, right? Do you understand? So this is the case, but we need to also think about the corner case, right? So what does that mean? So for example, so let us assume that the former instruction, like the former instruction is the store instruction, right? Then the and or instruction is the follow instruction. Then do we need to check the data boarding this case? Actually not, right? Because the store instruction does not write data to the register file, right? The store instruction just read data from the register file. So what does that mean? If the former instruction does not write data to the register file, then we don't need to check the data forwarding, right? So we need to check the regular write signal, right? So the forwarding is just valid if the former instruction write data to the register file. So which means if the regular write signal of the former instruction is 1, then the forwarding is valid. If the regular write signal is 0, so which means that the former instruction does not write data to the register file, right? Then we don't need to check the forwarding. So we need to add this condition, okay? So we need to check the regular write, okay? And then what is the corner case is if the RD is 0. So for example, this is the example, add x0, x1, x2, and then and x5, x0, x3, right? Then do we need to check the data forwarding? So you can find the data dependencies between this x0 and x0 of add and then x0. This is RS1 of end, right? So based on this condition, right, or this condition, then this is the data forwarding case, right? But we we must not check the data forwarding in this case, right? So what's the problem? So actually, even though the add instruction is executed, the result is not updated to the x0 because x0 is always 0, right? So actually we need to avoid the data forwarding for this case, right? So x1, so for add instruction may generate the x1 plus x2, and then this data may not be 0, right? And this is a non-zero value, right? But x0 is always 0 by definition, right? Based on the the instructions and architecture document, right? So actually x0 is to be 0, right? Always. But if the non-zero value is voided, then our CPU will generate the incorrect result, right? So if a CPU creates incorrect result from the code, we cannot use this CPU, right? Obviously, right? So we need to check this corner case is a special case, right? The destination register is to be non-zero value, right? So which means the register number of this RD should be non-zero. Okay, so this is the another condition. So this is the base condition, right? So we need to just check the RD of the former instruction and RS1 or RS2 of the following instruction, right? And then also we need to check the RD is valid, right? So we need to check the regulator signal, and we need to check the RD is non-zero. Okay, non-zero, so it's not zero, right? Do you understand? So this condition needs to be added in a data forwarding detection. Okay, so and then so let's see how the data forwarding is implemented. So we just learned about the two data forwarding paths, right? What is the first one? The first one is the memory stage to ALU, right? So actually the input of the ALU, right? Then second forwarding is the write back stage to ALU, right? The input of also the input of ALU. So we need to add this data forwarding path, right? In the pipeline's CPU, right? So so we need to add this data forwarding path. Okay, what is this data forwarding path? Is one. Okay, and then where is this is this one. Okay, this one and this one. Also, you can find the multiplexer here, right? So why this multiplexer is required? Because the ALU, so this is the ALU. The ALU can receive data from the register file, right? Okay, and then also ALU can receive data from boarding path, right? So, and then we need to select if the boarding is enabled, right? The boarding is required, then we need to select this data from the boarding path, right? And then this is the number one boarding, right? The boarding number one, okay? Then what is the second boarding? Okay, we change okay. So second boarding is the write back to ALU, right? Input of the ALU. So what is this path? This path is this one, and this one, this one, okay? So this is the second forwarding path, okay? So you can observe that. So this data is the data from this multiplexer. And then what is this multiplexer? This multiplexer can receive data from data memory and then data from ALU, right? And then this is the final write back data, right? So if this former instruction is the load instruction, the data can be generated from the data memory. And then, but if the former instruction is the R type instructions, like so, right? Then the data comes from ALU, right? And then, so we need to just select the data based on the instruction. So this is the final write back value. So for this second pass, so this value, so the output of the multiplexer needs to be forwarded. Okay, so in order to support the data forwarding, then we just added the hardware, right? So it's a the forwarding multiplexer, right? And then the data is transferred from it's a memory stage. So this is a yellow line, and then from the write back stage, it's a mint line, right? So we implement the hardware. So, and then, this is the multiplexer, and then multiplexer receive the control signal, right? It's a selection signal, right? So we need to generate this selection signal, okay? The selection signal is generated by forwarding unit, forwarding unit. So you can find the forward A, so it's a selection signal of this multiplexer, and then forward B, so this is the selection signal for this multiplexer. And then you can find that the forwarding unit generate these selection signals, right? So control signals. And then forwarding unit just to detect the forwarding cases, like the case number 1, case number 2. So in order to detect these forwarding cases, the forwarding unit receive the RS1 and RS2. And what is this RS1 and RS2? These RS1 and RS2 are RS1 or RS2 in EX stage, right? Because this is the output of IDEX register, pipeline register, right? So RS1 and RS2 EX. And then, as you can see, this is delivered, and then this is delivered. So what is this one? This is the RD. What is this one? This is the RD in memory stage, and this is the RD in write back stage, right? So it received these signals, and then forwarding unit generate the forward A and forward B signal. Okay, do you understand? So and then obviously the forwarding unit also received some these regularized signal, right? Regularized signal. Also, actually, the regularized in memory and regularized in write back needs to be also delivered to this forwarding unit. Okay, do you understand? So, do you understand? So I explained how to detect the forwarding cases and then how to apply, how to implement this forwarding. Okay, and then so we can just generate the MUX signal, the selection signal based on this definition. So forwarding, if the forwarding A is 0, 0, this is the normal case, right? Normal case. And then if the forward A is 1, 0, then it comes from EX and MEM. What does that mean? This is the data is forwarded from the memory stage. If the forward A is 0, 1, so which means the data is forwarded from the write back stage. Okay. And then the forward B is the same, right? So forward B is the same. Okay. So we can define the control signals, right? And then we also need to consider also the another corner case, the double data hazard. So what does that mean? So this is the example of a double data hazard. So which means, so this is the forwarding case one, right? So x1 needs to be forwarded to this x1, right? And then also we can find the another boarding case 1, right? For this add instruction, right? Because this x1 is to be boarded to this x1. But we can also observe the second boarding case is a board 2 because x1 can be boarded to the x1, right? So actually, if we focus on this add instruction, then we can find that this add instruction can have boarding case 1, both code boarding case 1 and boarding case 2, right? Then which data needs to be boarded? This x1 or this x2? Obviously, this x1 needs to be boarded to this x1, right? So for add this add instruction. Why? Because this is the latest value, right? So it is like this a equal b plus 1, and then another a is a plus 2, and then c equal a plus uh, 4, right? Then for this c needs to receive data from latest instruction, right? Obviously, right? Because the instructions are executed from top to bottom. So if the boarding case 1 and boarding case 2 are all valid, then we need to select the boarding case 1, right? Because boarding case 1 is the latest boarding. Okay, so it just bought the latest value, right? Obvious, right? Obviously, right? So we need, we need to also add this condition, right? So, so which means that if the if the even though the boarding case 2 is valid, but and then if the boarding case 1 is valid, then we need to select the boarding case 1, right? But so so in this example, so this is the revised so the boarding case, right? So we need to check the so boarding case the revised boarding case 2, right? The boarding case 2. So we need to check the regulate and then register is 0, is not 0, okay? And then so RD is RS1, then is 4D is 0, 1, so for the case 2. And then we also need to check that, oh, boarding case 1 is not valid. Then board case 2 is selected, right? So we can just think that, oh, the priority of boarding case 1 is higher than the priority of boarding case 2. Okay, do you understand? So we need to apply this, but actually it can be so when we design the control unit, then we can just simply implement this priority using the if else. So what do they mean? So I mentioned that the priority of boarding case 1 is higher than the priority of boarding case 2. How can you implement this? So firstly, we need to check the boarding case 1 first. Then if true, then boarding case 1 is activated. Otherwise, else, right? Then we can just check the boarding case 2. Then if it's true, then boarding case 2 is activated. Else, no more. Right. So if we just some statement using the if, else if, and then else if like this, then we actually the priority is naturally, so obviously determined by this order of condition, right? So actually this condition has the highest priority, right? So we can just implement this different priority of the boarding 1 and boarding 2 using the if else statement, right? So you know in the system Verilog also includes the if else statement, right? So and then which means that if we use the if else statement, then priority is actually uh, implicitly the priority is decided. Okay. Okay. So this is the completed design for data forwarding. Okay. And then also this figure also includes some control signals, right? So you can find the the regulate signal here, right? So regulate signal. Okay. 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 So this is the data forwarding. So uh, then if the former instruction is the R-type instruction, then the clock cycles are not wasted because we can just handle this data forwarding using data forwarding path, right? But if the former instruction is load instruction, then we cannot avoid, right? So just like this. So load word x1. So load word try to some update data to the x1. Then the following instruction, add instruction uses the x1, right? So in this case, the load word generate data in data memory, right? Then add instruction requires data in EX stage, right? So then which means that the add instruction needs to be stored. So store means that add instruction cannot be executed in the EX stage, right? So where is the case? So this case. So this is the load instruction. Load instruction generate data and then it will store data in X2. And then the next instruction is the end instruction, right? So when the load instruction is in the memory stage, the SCC4, then the end instruction, if the instruction is not stalled, okay, stall means that it's stopped, then end instruction is in the EX stage, right? But the end, in order to execute this ALU, then end instruction receive data before the ALU, right? So end instruction is to receive data from for the input port of the ALU. But actually, the load instruction is in the memory stage, and then the data will be generated at this point. But the data is necessary at this point, right? So data forwarding is not possible, right? So in this case, the end instruction cannot be executed in the EX stage, right? So we need to store this end instruction. So which means that the end instruction cannot be executed in the EX stage. So end instruction needs to stay. So cannot be propagated to the this EX stage. And this end instruction needs to wait in the ID stage. So this is called the pipeline stall. Okay, stall. Then if the end instruction is here and then it's just stopped, okay, it's just stalled, then how can we generate some signal? So we need to generate the no operation. Okay, so end instruction. So actually, end instruction needs to be propagated to the EX stage, but because of load use hazard, end instruction cannot be propagated. End instruction needs to stay in the ID stage. Then what will happen in the EX stage? EX stage will not do uh, yeah, so EX stage will do nothing. So do nothing is the nope operation. No operation. Nope or nope. It's called a nope or nope. So it represents the no operation. Okay. So instead of propagating the end instruction to the EX stage, end instruction stays in ID stage. No operation is just propagated to the EX stage. So because this is the no operation, so clock cycle is just wasted. Okay. So if the load use data hazard is detected, so firstly we need to detect, right? Detect. Then second, we need to handle, right? So if the load use data hazard is detected, then the following instruction stays in the ID stage, and then nope is generated. Nope is generated in the EX stage. Okay, do you understand? So this is the pipeline store. So pipeline store is implemented like this. Do you understand? So the firstly, we need to detect. So how can we detect? So first we need to detect the load use hazard. Okay. Obviously, in order to detect the load use data hazard, the formal instruction is load instruction. Okay, load instruction. So how can we detect the load instruction? So we can just check the mem read signal. Okay, and then this is the data hazard, right? Then we can just check the RD of load instruction and RS1 and RS1 or RS2 of the following instruction, right? So, and then, so the following instruction needs to stay in ID stage. So then, where should we detect this load use hazard case? It's simple. I mentioned that the following instruction needs to stay in ID stage. So this condition needs to be detected when the following instruction is in ID stage. So what does that mean? We detect this condition. Oh, the load instruction is a mem read, but mem read is in EX stage. So we need to check the mem read in EX. So this means the load instruction, and then we need to check the RD, and then also RD of the EX stage. Then we check the ID, RS1 and RS2 in ID stage. So this is the basic condition. The basic condition of load use data hazard, right? You understand? So and then also actually, so also we need to check RD is not 0, right? So mm, mm, okay. So then how to store? I already explained that when the following instruction, the next instruction is stays in ID stage. So it's a stay. The next instruction stays in ID stage. Then we need to generate the NOP, no operation in EX stage. Then how? So we need to generate the no operation. Okay. And then simply we can just make all control signals 0, right? So if the all control signals become 0, then it does nothing. The CPU does nothing. Okay, we can just we can make all control signals 0 in EX stage. And then also we need to just handle the instruction fetch stage. Why? Because the next instruction, the the next instruction, so this instruction in ID stage need to stay in ID. How about this instruction? Also needs to stay in instruction fetch stage, right? Right, because it the former instruction stays in ID stage, then follow instruction cannot be propagated. It needs to stay. Okay. So then how can we make the instruction in instruction fetch stage stay in the instruction fetch stage? We do not update PC, right? So in order to fetch the next instruction, then we need to update the PC, right? Like PC is the PC plus 4, right? But if we do not update the PC, right, then PC value is the same. So which means the same instruction can be read from the instruction memory, the same operation. So which means the instruction in instruction fetch stage stay in instruction fetch stage, right? So we can just disable the update of the PC for the instruction fetch stage. So by doing this, we can make pipelines stalled. Okay, so do you understand? So I already explained this. So it's stalled it here, and then obviously the instruction fetch is also stalled, and then no operation is generated. So when the load use data hazard is detected, then we need to control the pipeline, the CPU like this. So you can find the hazard detection unit here. So this hazard detection unit just to detect the load use data hazard, right? So and then you can find that this hazard detection unit received the RS1 and RS2 in ID stage, and then mem read in EX stage, right? And then it also received the RD in EX stage, right? You can find this line here. Where is the, oh, no, not this line. This line here, right? This is no. hazard detection unit. And then if the load use data hazard is detected, then the 0 is given to the makes it makes all control signals 0. Also, when the load use data hazard is detected, then PC write becomes 0. So which if the PC write becomes 0, then PC is not updated. And then it also becomes 0. Because the instruction is not propagated. So we can just disable the propagation of the instruction, right? So instruction fetch and ID stage pipeline register is also disabled. Okay, so this is the hazard detection. Hazard detection in pipeline CPU, right? Okay, so we learned how to implement the data forwarding in the pipeline architecture, and then how to implement the hazard detection unit in pipeline architecture, right? And then if the hazard is detected, then pipelines need to be stalled, right? And clock cycles are wasted, so which means performance is degraded, okay? And so we already learned about the compiler optimization like this. So if the compiler knows the structure of this pipeline architecture, then compiler changes the order of instructions like this, right? So we can avoid the the pipeline stalls by load instruction. Okay. Okay, so I will stop here, and then actually this part is very important, right? So as I mentioned, the pipeline architecture needs to support the data forwarding and hazard detection. So, and then when the hazard is detected, then the pipelines need to be stalled, right? So it needs to be also handled, implemented in the pipeline architecture, right? So you need to understand this. And then, so this is a little bit tricky part in the pipeline architecture. But because this is a little bit difficult, so you need to understand, right? Right? Okay, so I will stop here, and then so please watch this video, and then for the next class we will learn about the control hazard. Okay. Okay. Thank you guys, and then okay, and have a nice time.